Chapter 2, Trigonometric Functions. And now we're in section 2.5, the unit circle approach. So this is going to be a big brain stretch, so get your brain ready. So we're going to talk about the properties of the trigonometric functions on the unit circle. So the first objective is to find the exact values of the trig functions using the unit circle. The second objective is to know the domain and range of the trig functions. And this will become especially important when we get to talking about inverse functions. Then we need to use periodic properties. We'll talk about periodicity. Use the periodic properties to find the exact values of trig functions. And last objective is going to be to use even odd properties to find the exact values of trig functions. We need some kind of abbreviation for that. So first we're going to find the exact values of the trigonometric functions using the unit circle. So what is the unit circle anyway? So it's a circle with the center at the origin, pretend that's circular, that has a radius of 1. So let's think about where the points are where this unit circle meets the axes. So let's see, we'll have this point on the circle is going to be 1, 0. This point will be 0, 1. Negative 1, 0. And 0, negative 1. So you can see how the circle is situated. So since the radius is 1, let's see, the circumference is 2 pi r. That's the formula. So since the radius is 1, the circumference is 2 pi. So that means all the way around this circle, if I took a string and wrapped it around this circle and then laid it out flat, it would have a length of 2 pi exactly. So every real number t corresponds to a point on the unit circle that's a distance t traveled along the circumference of the circle. So if I have some point over here and I talk about a little creature that walked along the circle and I say, how far did the creature walk? It walked a distance of t. But because of this special r equals 1 of the unit circle, and s, the arc length, being r theta, well then s equals theta on the unit circle. So s is arc length and specifically refers to arc length, but we're going to use this number t as a variable that's talking about the distance traveled along the circumference of the unit circle, where t is a real number. But because theta in radians and r is 1 equals s, t and theta actually correspond to each other. Then we have a unit circle activity that we're going to do together in class. And the big idea about the unit circle is when we're at some point on the circle that we've traveled to, so let me just put one over here. So this is a point A, comma B. And we start at the positive x-axis and we walk along the circle a distance of t. So it's as we've traveled on the circle a distance of t. So if we took this string and laid it out flat, it would have a length of t. So these are the two ideas we're trying to connect. A linear distance, t, but then we wrap it around the circle of radius 1, and t and theta are actually going to be the same value because the r is 1. So every real number t 6, -42, 7/8 corresponds to a point on the unit circle that's the distance traveled along its circumference. So if we travel counterclockwise, we go to positive numbers, and clockwise to find points corresponding to negative numbers. So let's draw the right triangle formed by the center of the circle, the point P, and the x-axis. So this is a right triangle. We drop a perpendicular straight down from P to the x-axis. So we have a right angle with that perpendicular and the x-axis. And then notice that this hypotenuse is r, which is equal to 1. So because the unit circle has r equals to 1, the ratios we learned previously simplify for points on the unit circle. So the sine of the angle is going to be b, and the cosine is going to be a, and tangent is b over a, and then we have the reciprocals. Cosecant t is 1 over b, secant t is 1 over a, and cotangent t a over b. So remember that if a denominator is 0, the function is undefined. It's going to keep coming up in this class. So what do you notice about the sine of the real number t? So sine t and the y-coordinate of point P, O. They're the same. And what's the x-coordinate of P? A. And which trigonometric function does it correspond to? The cosine. So this might help you that cosine t, sine t, those are in alphabetical order. They correspond to the x-coordinate, y-coordinate, or you can call them a, b, of any point on the unit circle. And recall the difference between the values you can get for trig functions on the unit circle and the numbers you get if you're in the right triangle are that on the unit circle we can obviously get negative numbers for a and or b depending on which quadrant we're in. So depending on context, you can think of the argument as a trig function as either an angle, you could have the sine of theta, or a real number, you could have the cosine of t. And I'll give you some examples of when you would want which of those. So typically a Greek letter is used when we're referring specifically to angles, and a regular alphabet letter that we use all the time, that's what we use when the context calls for a real number argument for the trig function. So we'll work on these exercises together. And let's look at objective 2, where we need to know the domain and range of the trig functions. So let's look at their definitions. I've repeated them here so you can see. And when we're talking about domain, we're talking about, are there any restrictions on the values of theta that we put in to the trig function? And it looks to me like we can put any number we want in there because we can find the values of trig functions for any value of t as long as those denominators aren't 0, right? So the domain of sine and cosine are going to be all real numbers because I can put any number in there I want and find its sine and cosine. Now tangent's trickier because if I try and find the tangent of, let's see, tangent is sine theta over cosine theta. If I try and find the tangent of an angle where the cosine is 0, I'll be in trouble. So I need where cosine isn't 0. So let's think about where it is 0. So we have cosine theta, sine theta, AB. So we need A not to be 0. So we need the x coordinate not to be 0. So we can't have this angle or this angle. So it looks like tan theta, the domain, we have to exclude theta equals, let's make a little list here, pi over 2, 3 pi over 2, 5 pi over 2. Oh, this is looking like odd multiples of pi over 2. So theta can't be, this is where we're going to come and use our k notation. Theta can't be 2k plus 1 times pi over 2. So this is how we say odd numbers. Because if you think about, if you do 2k, that's how you make an even number. If you multiply by 2, guaranteed to have an even number. And then if you add 1, guaranteed to have an odd number. So can you see that this was, if I distribute, this is the same thing as k pi plus pi over 2. So that's another way of thinking about it, is that the first one is pi over 2, then you add pi to get to the next one, then you add pi to get to the next one, add pi to get to the next one, and so on. So theta can't be odd multiples of pi over 2 to get a valid result for the tangent. So do you see that that's going to be the same restriction as for secant? Because they both have a on the bottom. So a can't be 0. So this is tangent and secant have the same domain restriction. So then let's think about cosecant. Let's see, we want b to not be 0. B corresponds to the sine of theta, and it's the y coordinate. So we want the y coordinate not to be 0. So we don't want this angle, which is 0, and we don't want this angle, which is 180 degrees or pi radians. So then this keeps happening every time we go pi around. So it looks like now we have to have theta not equal to k pi. So any multiples of pi aren't going to work well. And notice that that's going to be the same thing as for the cotangent. So the domain of cosecant and cotangent theta is theta can't be k pi. So we have the domains for everybody. So now let's talk about the ranges. So we can see that sine theta and cosine theta, again, can be any real number as the output. A and B are real numbers. But you can see that, oh, let's see, sine corresponds to the y coordinate and cosine corresponds to the x coordinate, but we're on this unit circle. So what's the biggest number x can ever be? 1. And the smallest number it can ever be is -1. The biggest y can ever get is 1. And the smallest it can ever get is -1. So the range for sine and cosine is from -1 to 1, and that's as far as you can get. You can't get any numbers bigger than 1 or smaller than -1 as the outputs or the result of a sine and cosine function. So then tangent theta, let's see, what range would we get for that? Well, let's see. As long as a is not 0, it's looking like you could get any number you like for the output of the tangent. So then because we have reciprocals going on, let's see, if I take the reciprocal of a number that's between -1 and 1, but now I'm doing 1 over that number, now I actually get from -infinity up to -1, and from 1 to infinity. So I'll let you think about why that would be. And that's the same thing as for secant theta. That's the range for the secant of theta. Because if you have numbers that are between -1 and 1, and then you do their reciprocals, they get bigger. So think about why that works. And then, of course, cotangent is going to be the same range as tangent.